Hello there and welcome to my channel on chemistry lessons. At the moment we do predominantly focus on A-level chemistry lessons and they are designed to be full lesson videos. So please make sure you subscribe and you like to make sure you don't miss out on future videos. I do aim eventually to cover the full A-level specification. If you think there are any gaps, please let me know and I'll ensure that I fill them for you. So hopefully you find it useful and good luck. So this is an alkenes topic then. This is an alkenes lesson and it's the first lesson of the alkenes A-level topic. We're going to look at the bonding in alkenes. So we're going to look at that double bond and how that leads to geometric isomers, the Zed Isomers. The spec makes it look so sweet and straightforward. It basically just tells you that they're unsaturated hydrocarbons, which you probably can remember from GCSE. Unsaturated means it has a carbon-carbon double bond, and the only thing that appears to be new here really is that it tells you it's a center of high electron density. So we will look in detail at what the difference is between a single bond and a double bond, and we're also going to look at how that leads to geometric isomerism and eventually how that double bond will cause the reactivity in these alkenes. So we're probably familiar already from GCSE that an alkene is a carbon double bonded to a carbon, and they have the general formula CnH2n, and that shows that it's unsaturated. It has a carbon-carbon double bond. Now, the first misconception that people will have coming from GCSE is they will think that a double bond is just the same as two single bonds. And it's definitely not. There are two types of covalent bonding going on here. And you can see that I've labelled or named the two types of bonds as a sigma bond or a pi bond. We can use the symbol for sigma and the symbol for pi, or we can call them sigma and pi. Now, a sigma bond, a sigma covalent bond, is the most common type of covalent bond. That's when the pair of electrons being shared is directly between the two nuclei. So we know that a definition for a covalent bond is the electrostatic attraction between a shared pair of electrons and two nuclei. And that is correct for all covalent bonds, whether it's sigma or pi. But a sigma bond is when the shared pair of electrons is directly between the two nuclei, as a result usually of the overlap of these s orbitals. So you can see that they're directly between the two. Now, a pi bond is different to a sigma bond. A pi bond is a result of our p orbitals. So if you recall your knowledge on orbitals way back at the start of first year, we had p orbitals and they kind of looked like this. We called them dumbbell shape. Now what can happen is when these electrons are involved in bonding, these p orbitals will overlap, and what we end up with is an area above and below, and the electrons are found in these electron clouds. So the electrons are shared in these overlap of p orbitals. Now I'm only drawing it two-dimensional. This would be a three-dimensional. You could imagine it kind of like wrapping around. So we have these two electrons in a pi bond and a sigma bond. So a double bond is in fact a pi bond and a sigma bond. Two types of bonding. The pi bond is the overlap of p orbitals. So we have two pairs of electrons being shared in this double bond. We have 4 electrons here in this double bond, which is why it's an area of high electron density. A double bond is an area of high electron density. We saw that in the specification. So 2 key things to take away from a carbon-carbon double bond. Number 1, it's an area of high electron density, so there are more electrons in a double bond than you're going to find in a single bond. That's possibly obvious, but it is an area of electron density. And also the second thing to take away is that a double bond is locked. There's no free rotation. They can't spin or rotate. And the opposite can be said for a sigma bond. So for these sigma bonds here, they can actually rotate. Kind of imagine if you've made a molymod, the single bonds you can kind of rotate and flip around. This double bond is locked. You don't get any rotation. There is no rotation. And that's quite important because that gives rise to isomers, to geometric isomerism. Now, geometric isomerism is when we have the same structural formula but a different arrangement in space. And the simplest example I can give there is something like this. That's a CH3 group and a H. So this is but2ene. It's butene with a double bond between the second and third carbon. So that's but2ene. And on the right hand side, I'm also going to draw but2ene. However, you can see that those two methyl groups are on opposite sides, opposite ends. We have the CH3 at the top and then the CH3 at the bottom on the right hand side, and on the left hand side we have the CH3 at the top, both of them at the top. Now, because we don't get free rotation, this can't just rotate and be the same as the other one. They are definitely different. They are classed as geometric isomers. They have the same structural formula, which in this case is CH3, CH, CH, CH3. And if I do the structural formula of the one on the right, it's exactly the same. CH3, CH, double bond CH, CH3. But they are definitely not the same thing. If we were to make these with molymods, they are non-superimposable. They have a different arrangement in space. So we need to come up with a way of naming these isomers. So let me draw these two again for us. And we use the CIP rules, and you do need to be able to assign CIP rules. So I'm just going to draw the two isomers out again. Here we go. Now what we do is we identify the double bond first. So let's identify the double bond. And let's draw a line through that double bond. Now I'm going to look at the left hand side on both cases, and I'm going to assign a priority to one of the groups. We have two groups. On the left hand side we have a CH3 and a H, and that's the same in both examples with a CH3 and a H. Now what we do is we look at the atom that's bonded to the carbon. So in this case it's H, and in this case it's C. And again it's C and H. And what we do is we look at the atomic number of that atom. This has an atomic number 6. This has the atomic number 1. We use the periodic table to find the atomic numbers. Oops, why am I writing H? It's 1. And what we do is the highest wins. Simple as that. So this wins gold medal, and this has come second. So there's always a first and a second place. First, second. So we've awarded first place here and second place down here. First place up here, second place down here. Now we're going to go through the same reasoning, but this time I'm going to look at the right hand side. So I'm going through the same logic. On the right hand side we've got a carbon and hydrogen. This is atomic number 6. This is atomic number 1. 6 wins, that's the highest. So the highest priority is there, the second priority is there. I'll apply the same logic here. We've got hydrogen, which is 1, carbon, atomic number 6. 6 is higher than 1. So the number 1 priority is here, second priority is here. Now what we do is we look, and if the high priority groups are on the same side, as in here, look, so the number 1 priority is on the same side here, this is called the Zed Isomer. Now my understanding is the Z comes from zusammen in German, which means together. So the Z is zusammen, together. And if the number 1 priority groups are not together, they're opposite, as they are in this example here, they're opposite, that is the E isomer. Now again, I believe that is entgegen, which means opposite in German, but someone can correct me if you think I'm wrong. So that's our E and Z isomers. So assigning priority rules based upon the atomic number. So let's look at a slightly more difficult example then. So this one is slightly more difficult. So let's talk through the rules again. So let's draw that line through that double bond. And then let's just look at the right hand side to start with. The right hand side is fairly straightforward. We've got the atomic number 6 and the atomic number 17. 17 wins hands down. So number 1 is at the top, number 2 is down the bottom. Let's have a look on the left hand side. We've got the atomic number 6 and the atomic number 6. Problem. Okay, so there's a tie. Then what we do, if it's a tie, they're going to go to the next biggest down the line. So in the case of the carbon at the top, it's a carbon bonded to 2 hydrogens, but another carbon. So let's go to the next biggest. So it's 6, 6, this one. The CH3 group, it's 6, and then the next biggest we can find is 1. So it's lost in a playoff, this. So this has come second, and this is number 1. So now we find that our 2 number 1s are at the top. They are together, zusammen. So this is the Z isomer. Okay, I'm going to suggest you pause the video now and then you try and do these two yourself. Identify them as E or Z isomers, applying our SIP rules. And when you're ready, unpause the video and see if you got them right. Right, let's start over here on the left then. So draw your line through the bond. On the right hand side, number 1. Hang on a minute, what am I doing? The right hand side has atomic number 1 and this has atomic number 9. 9 wins. So number 1 priority is down the bottom. Left hand side, atomic number 17 and atomic number 9. 17 wins. So number 1, number 2. So we have opposite here. This is E, the E isomer. Entgegen. Don't need to know the Entgegen zusammen, it just helps us remember them. So this is the E isomer on the left. Right hand side, draw a line. I'm going to start on the left here. Atomic number 9, atomic number 12. Atomic number 6. Not 12, that's the mass. So it's atomic number. And again, it's quite common for students to ask me, so you know, some textbooks and some revision guides will state it's mass, it's not. It is atomic number. So 9 does win. 9 wins. Number 1 is at the top. Number 2 is down the bottom. And I've been a little awkward on the one on the right because we go 6 and 6. It's a tie. The next biggest on the bottom is 6. The next biggest is bromine, which I'm now closing my eyes and I can't remember, but it's much bigger than 6. I know for a fact. I don't have a periodic table, I know the mass, but it's definitely bigger than 6. So don't know what it is. You can be smug and find out, but that's definitely bigger. I'm confident it's bigger than 6. So number 1 is at the top. So this is the zusammen, the Z isomer. And that's the introduction to alkenes all sorted, which is looking at the double bond, being aware it doesn't rotate, and that's what gives rise to your stereo isomerism, your geometric isomers. So look out for lesson 2, which is going to start looking at the reactions of alkenes. Subscribe and you won't miss out.